In this video, we're going to do the same example as the previous video, the 11.2 Gaussian elimination, except this time we're going to use matrices to solve it. And we're going to do what's called full Gauss-Jordan elimination. So instead of just getting ourselves to a triangular matrix, we're going to go into a diagonal matrix. So we'll have ones down the diagonal, zeros both up here and down here. So the first step, of course, is to turn this into an augmented matrix. We do that by just reading off the coefficients. So the coefficient of x is 1, the coefficient of y is -2, the coefficient of z is 1, and the constant is -9. We put a line here usually to distinguish that, and then we do that with each row. My 3's are being a bit of a problem today. And now we follow the same basic pattern we did for Gaussian elimination. We start, first goal is to get a 1 up here. Since we have that, we move on. The next goal is to get zeros down here. And we will do that by taking -3 times row 1 plus row 2 and 2 times row 1 plus row 3, sorry. Again, notice we are not changing row 1. It appears here, not here in the second part. So row 1 will stay the same. But what we're going to do is change rows 2 and 3 by taking this minus 3 times that. 3 minus 3 is 0. In the matrix, we do have to include the zeros. -3 times -2 is +6, so 4 plus 6 is 10. -3 times 1 is -3. 5 minus 3 is 2. -3 times -9 is +27, so 9 plus 27 is 36. And now we're going to take 2 times row 1 and add it here. So -2 plus 2 is 0. 2 times -2 is -4, plus 3 is -1. 2 times 1 is 2, plus -1 is +1. 2 times -9 is -18, plus 12 is -6. Now again, our next goal is to get a 1 right here. And while we could multiply this row by +1/10, it'll be easier to multiply this row by -1 and move it up here. So I'm going to take row 2 and swap it with negative row 3. Row 1 isn't changing. My handwriting's getting worse though. And we're swapping these rows. We're negating row 3. So 0 stays 0. -1 becomes +1. +1 becomes -1. -6 becomes +6. Row 2 isn't changing. It's just moving down here. So we have 0, 10, 2, and 36. And now, since I'm doing Gauss-Jordan elimination, trying to get zeros everywhere, diagonal matrix, not only do I want this to be a 0, but it would be nice to make this a 0 in this step. So, in order to make this one a 0, I'm going to take -10 times row 2 plus row 3. In order to make this one a 0, I'm going to take 2 times row 2 plus row 1. And now we see row 1 is changing. So let's go ahead and change it. Well, that 0 is not going to affect the 1. That's why I got these to be zeros first before I started playing with this. By making these zeros, I won't affect this 1, which is important. Now I take 2 times this plus -2 is 0. 2 times -1 is -2, plus 1 is -1. 2 times 6 is 12, plus -9 is +3. Row 2 is not changing. It's only rows 1 and 3, so we'll leave row 2 the same. Then row 3, I'm taking negative 10 times this and adding that. So negative 10 plus 10 is 0. Oh, the zeros don't change. That's a 0. Negative 10 times 1 is positive 10, plus 2 is positive 12. Negative 10 times 6 is negative 60, plus 36 is negative 24. Now our next goal is to get a 1 down here. We'll do that by just taking 1/12 row 3. Rows 1 and 2 aren't changing. But these rows, 1/12 times 12 is 1, 1/12 times 24 is negative 2. Now finally, to finish Gauss-Jordan, I need to have these be zeros. And that's really nice in this case because they're both negative 1, this is a positive 1, so all I have to do is add row 3 to each of these rows. This will give me, let's see, row 3 plus row 1. And row 3 plus row 2. Row 3 is not changing, so I'll come back to that later. Row 1, though. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus negative 1 is 0. Negative 2 plus 3 is 1. Row 3 plus row 2. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus negative 1 is 0. Negative 2 plus 6 is 4. And then, as we said, row 3 is not changing. Nice thing is this has now given me 3 equations. This top one really says x equals 1. Well, really, x plus 0y plus 0z equals 1. This next one, 0x plus y plus 0z equals 4. And then finally, 0x plus 0y plus z equals negative 2. And now, since we want an ordered triple, we just turn that into an ordered triple. And there's our solution.